Okay, let's start our lecture. And today we discuss functional limit theorems for scaling limits of perturbed random walks if a membrane is two-sided. And the main example that we will consider will be random walk with transition probabilities on Z with transition probabilities 1/2 from I to I plus or minus 1. So we make the unit step up or down everywhere except of 0. And from 0, you jump up with probability p and jump down with probability q, where q is 1 minus p. If p is 1, then we have just reflected random walk, and we know that the limit will be reflected Brownian motion. In this case, the process will be more interesting. So we walk up and down with probability 1/2, but here we jump either up with probability p, and then we continue with probabilities 1/2 going up and down. And if you go down, so every time here you toss a coin, and with probability p you go up, with probability q you go down. Okay, but before we start formal calculations, the question is how to describe a process that will appear in a limit. So I have more general question. How it is possible to describe stochastic process? Well, we knew a few possibilities. For example, we described a Brownian motion as a Gaussian motion with certain mean and certain covariance function. So we discussed finite dimensional distribution of a process. Then we discussed Skorokhod reflection or generalized Skorokhod reflection, and we constructed a new process as a function of an old process. Here we have a Markov chain. So it's natural to expect that the limit process, if it exists, also possess some sort of Markov property. I'm not sure that all students have studied Markov, the rigorous definition of a Markov process. So I will recall the definitions and make an analogy with Markov chains. So when we study Markov chain, we have like a basic object, a transition probability in one step. Yes, we study Markov chains, time homogeneous Markov chains. So Pij is probability that Px n plus 1 is j if xn is I. So you jump from I to j in one step. Then we introduced transition probability in k steps, like Px, so let me write, okay, n plus k is j if xn is I. We introduced matrix of transition probabilities in one step and k step, and if we know initial distribution of Markov chain, then finite dimensional distributions of the Markov chain can be written as follows: that probability that x of 0, say, is I0, x at the point k1 is A1, x at point k2 is I2, and so on. X k sub n is In is equal to initial probability times transition probability from I0 to I1 in k1 steps, then from I1 to I2 in k2 minus k1 steps, times so on, times probability that you jump from In minus 1 to In to if you use kn minus 1 steps. So if you know this, then you know this. And if you know initial distribution, then probability is just a product. Okay, and sometimes the Markov property is written in the following manner, that probability that xn plus k is equal to j, given that x0 is I0 and so on, xn is In. So the moment n we'll call, so it's like current moment, this is past, and this is future. Then if you apply these formulas, it's easy to see that this probability is equal to probability that xn plus k is j, given xn is In. So future depends only on your current position and is independent of the past, of all the past. Well, if you write this definition, you have to be careful in the following sense. Well, if this event is event of zero probability, then conditional distribution is not well defined. So you have to say, well, if this is not zero, then you have this equality for all. And usually people start studying Markov chains. They write this definition, introduce this Pij, and then deduce finite dimensional distributions. However, you may start from this formula and then get this almost for free. Okay, now let us consider stochastic processes with continuous time that are real valued. So usually when people study Markov chains, then they start from state space that are discrete values like integer numbers or natural numbers or just finite amount of states. Okay, so let's make an analogy in this. So I'll give you some sort of definition of Markov property in this situation. So this will be Markov process. We will say that xt is a Markov process with a transition density PTXY and that start from x0, that starts from x0. If so, this means that x0, if the random, if for every t1 tn, t1 less than t2 less than tn, random vector xt1 and so on xtn has a density, has the following density. Oh, let me write pt1 and so on tn x1 xn is equal to some sort of this product. So you start from, so we don't consider initial starting point 0. So if you write like conditional probability, then you just divide by this. And the density of this vector should be a product pt x0 x1 times p t2 minus t1 x1 x2 and so on ptn minus 1 minus tn xn minus 1 xn. So in some sense you have certain independence. You may ask me the following question. Okay, and how to write the first one is this. What is the analog of Pij? Transition probability, transition density in one step. The answer is no. I cannot do this. I can't determine one simple function such that all other transition probabilities can be calculated using this one. So you have to have a family of transition densities, and okay, for every x, ptxy should be density in y and measurable in pair x and y. The second question. Okay, we have this analog of this formula like a product. The question is, if you have some family of functions that are measurable in x, y, that are density that are non-negative, so the density is as a function of y, and we write this object. Is this a density of a certain stochastic process? The answer is generally not, and transition probabilities of any Markov chain satisfies so-called Chapman-Kolmogorov equation that states the following. For every n and m probability that you arrive from point X to point Y in n steps. Okay, on one hand, it's equal Pn for Markov chain, Pn xy, or xn plus m xy, or you may do the following: fixed m, and then arrive to point K, and then go to Y, and then consider a sum, okay, Z, and then consider sum over all Z's. So it should be sum over all Z in state space, probability that you arrive to Z in n steps, and then you start from Z and arrive to Y in m steps. For all X, Y from the state space, and for all n and m, non-negative integers. And the corresponding family of densities satisfies Kolmogorov theorem if these densities satisfy analog of Kolmogorov-Chapman equation. Namely, for every S and T positive, for every, if this is satisfied, for every X and Y real numbers, if you have ETX plus S X Y is equal to, we replace some with integral PT XZ PS ZY dz. Then there is a process x of t that satisfies such that this function is describes its finite dimensional distribution, and moreover, if you write if you consider conditional probability that x t plus s is in the set A, given sigma algebra generated by the past x z less than or equal to t, then this conditional probability is equal to probability that x t plus a belongs to A. Oh, okay, I have to write given sigma algebra generated by random variable xt, where t is the last point of the interval 0 t. So, well, in some sense, you may write that probability that xt plus a in A, given that x z1 is x1 and so on, x z. So take arbitrary set of indices, t1, t2, tn is n, and this conditional probability is equal to probability that xt plus s in A given xt is xn, well, and this equals probability that integral over A p, so amount of time s from this point to this point, ps xn y dy. However, you have to be very careful because now the distribution of this vector has a density, so it's a zero probability that x equals this is equal to these points. So you have to say that for almost all that this, you have to find regular conditional probabilities and then say that, well, for almost all points you have this equality. So you have to at least to think about this to this definition. Well, and general definition of a Markov process is this. So you need a family of stochastic kernels. Well, we consider real valued. So A is Borel set, X in R, T greater than T is greater than 0, A Borel, and we assume that for fixed T and X, PTX is a probability measure in A. If A is fixed, T is fixed, then this function is measurable in X. And we assume that P satisfies Kolmogorov-Chapman equation. This means that integral of Px dz Pza equals Pt plus s x a, or all x real, ts positive, a Borel. So informally, this means that you start from x, then you jump to the point z, and then you hit the set A, and then you sum up over all possibilities over all z. And this summation, this integration is equal to probability that you hit A, hit this set A in t plus s seconds starting from x. And it's known that if you have this object, if you have such probability kernels that satisfy this Chapman-Kolmogorov equation, then for every probability measure mu, you can construct the process probability measure. You can construct stochastic process xt such that mu is its initial distribution and probabilities, so finite dimensional distribution of x0, xt1, xtn can be written similarly to this formula. So what is the probability that x0 belongs to set A0, A1, and so on, AN? You have to consider sums over all I0 in this, I1 here, IN there. And in continuous situation, you have to replace sums with integral. So integral over A0 mu dx0 of, so maybe, and then integral over A1 and so on, integral over AN. So mu dx0 and then p t1 x0 dx1, so on, p tn minus 1 xn minus 1 dxn. Well, to be honest, we have to write like this. We fixed n minus 1 and integrate this over an. Then we obtain a function that depends on xn minus 1. Then we fixed xn minus 2 and integrate with respect to dxn minus 1 and so on and so on and so on. And the last integral will be with respect to x0. Okay, so this is construction, and it can be proved that if P satisfies Chapman-Kolmogorov, the process exists, that the process possesses some sort of Markov property. I will not state it. And well, it's analogy with Markov chains. Well, you may ask me, what are examples of Markov processes? And is it possible to find these or verify? Well, the first example is all processes with independent increments are Markov processes. And for example, in particular, Brownian motion. And in case of Brownian motion, this measure, this transition kernel has the following form, where this transition density is Gaussian with variance t, where phi t of z has this form, y minus x squared over 2t. T greater than 0, x and y are real numbers. Oh, excuse me, that I need to write Gaussian density here. And Chapman-Kolmogorov equation is just a fact that sum of two independent Gaussian random variables is again a Gaussian random variable, and you have to add means and variances. So this is interesting exercise to check this. Another example is reflected Brownian motion. It also has Markov property, reflected Brownian motion, and we discussed that if we consider the process x plus w of t, absolute value, this is some sort of Skorokhod reflection, and let's calculate not, so let's find density of this process at the point y. And the density of this process at the point y is equal to phi t y minus x. So the density of usual Brownian motion plus phi t of y plus x. And if you make a picture, so this red function is trajectory of usual Brownian motion. So started from x. And this blue is absolute value. And this density is equal to this, the density of usual Brownian motion at this point plus the density of a usual Brownian motion x plus wt at the point minus y. And if you remember formulas for reflected random walks, we have similar formulas for the random walks that has jumps plus minus ones everywhere except of 0 and reflects from 0 to 1. It jumps from 0 to 1 with probability 1. The exercise is to check that this process is Markov and to verify Chapman-Kolmogorov equation for these functions. X, y is positive, t greater than 0. Okay, and now I return back to this perturbed random walk. So we jump everywhere. We jumped plus 1 or minus 1 everywhere with probability 1/2 if I is not 0. And from 0, these probabilities are p. Probability go up and q probability going down. The question is, what is the limit of this as n tends to infinity? We know that if p is 1/2, then if we fix t, then we obtain Gaussian distribution in the limit. And the question is, what will happen in arbitrary case or arbitrary p? But at first, I want to find transition probabilities of this perturbed random walk. So the question is, find the distribution xn is y, conditional probability if you start from x. So this point is y. This instant is n. Okay, one moment. It seems to me that Gennady is joining, so let's wait. Oh, hello, Gennady.
Oh,
So now we discuss the following question. So I'm happy to see you joining. That we consider the following random walk. We start from x. It's integer valued random walk. You may jumps 1 or -1 with probability 1/2 everywhere except of 0. And from 0, you go up with probability p, and you go down with probability q, which is 1 minus p. And my question is, what is the scaling limit of this random walk? And at first, I wish to calculate transition probabilities. Well, some particular cases, if p is q is 1/2, then this is just simple random walk, simple symmetric random walk, and we know that in this case, transition probabilities from x to y in f steps, they depend only on n and on difference x minus 1, y, where phi n of z and n are integer numbers, are equal. So we calculated them. So like 1 1/2 to the power n, and then n choose n plus that over 2. If n plus that is even number, and that absolute value of z is less than or equal to n, we calculated the number of paths from x to y, and the number of paths from x to y is equal to this number, and probability that you go along every path is 1/2 times 1/2 times 1/2 is 1/2 to the power n. Well, and 0 otherwise. And we also have studied the case when p is 1 and q is 0, and this means that you reflect at 0 always up with probability 1. And maybe, Vadim, Gennady, maybe you remember the formula for Pn xy. Or at least the name of the method, how we deduce it.
reflection principle.
Yes, it was an reflection, Andre's reflection principle, and the formula was this psi n y minus x plus psi n y plus x. Yes, we considered So we associate with so the problem was to calculate the number of paths from X to Y, and some paths were from X to Y that didn't hit zero, and another were of unperturbed random walk, and another were a path that hit zero, and we calculated. We see that the number of paths that hit zero and ends at y are equal to the number of paths that start from x and ends at negative y. And after summation, we got this formula. Okay, and now the general result. The formula for arbitrary p, and the theorem is uh, probability uh, probability that you start from x and finish a conditional probability that you finish at x in n steps given that x0 is x is equal to transition probability of unperturbed random walks. So here y minus x, so y is this. So actually y is probability that Sn is equal to y minus x, where Sn is xi1 plus xin, where all xi's are id, independent identically distributed random variables with transition probability with this distribution, plus and minus 1 with probability 1/2. Then plus p minus q sine of y times transition probability in n steps of unperturbed random walk. But you have to write here absolute value of x plus absolute value of y. So x and y are integers, and is natural number. Before I prove this result, let us discuss that this formula is indeed that it coincides with these formulas for reflected and for unperturbed random walk. Well, if p is q is 1/2, then this term disappears, and you see unperturbed random walk. If p is 1 and x and y are greater than or equal to 0, then p minus q is 1, sine of y is 1, absolute value of x is x, absolute value of y is y, and we get this formula. You may ask me the following question. Well, and I write this formula for all x and y for all x and y. And here I write, I told you that, well, we discussed this problem and we have this formula only for positive x's and y's. This is true. But if x is negative, for example, and y is negative, what does it, what this formula mean? This formula means that the random walk that jumps from 0 to 1 with probability 1. And if you start from x, how can you come in y? This means that you never visited 0 and arrived to y. So you start, so this probability coincides with probability that unperturbed random walk start from x negative and at y negative and never hit 0. So in this case, well, if p is 1 and if x and y are negative, then probability is this: psi n y minus x plus p1 q0 sine of a negative 1, so minus psi n absolute value of x plus absolute value of y, so minus x minus y. But this function is symmetric, so we may write this. And we have seen this probability. This is probability that is indeed that you start from x, you finish at y, and never hit 0. And if, for example, x is negative and y is positive, well, or x is positive, y, oh, okay, let's consider this first case, and y is this more simple case. What is the formula? Psi n y minus x, p positive, so p1, so plus 1, sine y minus, then psi n x positive, so x, y negative, so absolute value of y is minus y, and we know that this function is symmetric, so this is 0. So we see that in case of reflected random walk, this formula is true. And we have discussed this formula a few months ago. Okay, let me also rewrite this general formula for different x's and y's and discuss it. At first, let x and y be non-negative, then sine of y is 1, and we have formula psi n y minus x plus p minus q. By the way, p minus q is equal to 2p minus 1. So sometimes people write it like this, sometimes people write it like 2p minus 1. So q is 1 minus p times psi n x plus y. If x is positive, y is negative, the formula is psi n of y minus x plus 2 pi minus y. Sine of y is negative 1, so minus times psi n. Absolute value of x is x. Absolute value of y is minus y. And this function is symmetric, so this function is equal to psi n y minus x. And this minus this is equal to psi n x minus y times what? Times 1 minus 2p minus 1 is 2 minus 2p, so 2q. So 2q psi n of x minus 1. Well, if x is negative, y is positive, then the answer is sine of y is plus times psi n. X is negative, so absolute value of x is minus x plus y is positive plus y. And the answer is psi n y minus x times 2p minus 1 plus 1, so 2p. Okay, it's all the same to write x minus y or y minus x. The function is symmetric, and if x is negative and y is negative, then the formula is psi n y minus x. Sign is negative, so minus 2p minus 1 times psi n, and absolute value of x is minus x, absolute value of y is minus y. The function is symmetric, so I may write pluses. So these are the cases. These for different values of p and q. So I will prove only this and leave all other three cases as an exercise. So we assume that x greater than 0, y greater than 0, and we want to find the probability that if you start from x and you finish n and y. There are two possibilities. The first possibility is this. You start from x, you don't touch 0, and you end at y. And the second possibility is this. You start at x, you walk like a simple random walk. Maybe you hit 0 one time or many times, and then you end at y. Okay, and let me consider the case when they're strictly greater than that, they're natural numbers. So xn is y, and x1 is positive, xn minus 1 is positive, plus probability that xn is y, and there exists k between 1 and n such that xk is 0. One of these two probabilities is easy to calculate. Which one? Vadim, Gennady? We can easily find one of these two.
One of them is 0, I think.
Excuse me? I didn't hear.
Is one of them 0?
No, no. You see, there may be. So the first possibility is you don't hit 0 and arrive to y, and another possibility that you hit 0 and after that you arrive to y.
The one where we hit 0.
I'm not sure that it's easier. The first one. So
Mm.
let me write like I1 plus I2. You see, jumps here have probability so if you don't hit 0, then the random walk behaves like a standard simple random walk. So the first probability is equal to probability that simple random walks that start from x ends at y and never visit 0. And you see, if you don't visit 0, then you multiply, then okay, probability of this path is equal to 1 divided by 2 to the power n. So probability that you arrive to y and never hit 0 is equal to 1 divided by 2 to the power n times the number of paths from x to y that do not hit 0. So, and this probability coincides with probability that simple random walk that starts from x never hit 0 and arrive to y at instant n. We calculated it, and the answer was psi n y minus x minus psi n y plus x. And the picture was this. So this is probability that simple random walk ends here, and we subtract probability that simple random walk ends at point minus y. And okay, so if you have some path that starts here and excuse me, and it ends here, then after reflection, you see a path that finish here. So amount of path that start from here ends here is equal to amount of path that hit 0 and ends here. So it's just a reflection principle, and we discuss it. And we are left to, so we need to calculate A2. So probability that perturbed random walk hit zero, and ends at y. Well, and let us take a look here. So we know the answer. So let me rewrite the answer. So this sum should be psi n y minus x plus 2p minus 1 psi n y plus x. So we have to prove this. We know that I1 is equal to this. So we need to prove that I2 is equal to 2 pi times psi n y plus x. Okay, you start from x. Sometimes you have a moment that you hit zero, maybe different times, and then you arrive to y. So we need to show this formula. And now let us consider the process. Let's calculate the following auxiliary probability, or let us discuss the process x n greater than or equal to 1. So absolute value of x. And I would like to state that this is reflected simple random walk. Random walk with transition probabilities. Okay, so let me write. Okay, so let me write here tilde. Probability from. So I will write the answer, and the small exercise is to prove that the answer is true. So the Markov chain X. So it has transition probabilities 1/2. With probability 1/2, you jump up and down if you are not at zero. So it's natural to expect that if you take absolute value and if you are not at zero, then you jump with probabilities 1/2 up, one unit up or 1 unit down. And if you are at zero, and if you consider next step, then either x goes down or if it goes up, the absolute value, okay, let me make the picture. So you just reflect, you always go up. So probability that you go to 1 from 0 is 1. So, well, it really can be easily seen that if you consider absolute value of perturbed random walk x, then you see just reflected random walk, and that with you start from if you start from 0, then you jump 1 unit up with probability 100%. And now let us compare probability that x hits 0 and then arrive to y, and probability that absolute value of x hits 0 and then arrive to y. Okay, I wish to write somewhere. Okay, let me. So let's calculate this probability. Let's calculate this probability. Okay, we know the answer, and we remember that x and y are positive. We know that for reflected random walk, the probability is psi n y minus x plus psi n y plus x. But now let's compare this probability with probability for x. Well, at first, it's obvious that we may write here x0 without modulus. Then we also know that modulus is 0 if and only if x is 0. So we have the following problem. So we start here, and we hit 0 sometimes, but at the end, modulus is equal to y, and this means that xn is y or minus y. Well, and mm, let us consider two probabilities. So this red function is trajectory is a path of x that hit 0 and arrive to negative y, and another path. So let me make it green. So the same until the last visit to 0, but then go up. What is the ratio of probability that you end here and the probability that you end here? So what are you doing? How we calculate probability? You multiply by 1/2, 1/2, 1/2, 1/2, 1/2, again, again, again. If you go down, you multiply by q, this red path and green path, then multiply by 1/2 p, and so on and so on and so on and so on up to this point. If you consider green path, then you multiply here by q. If you consider red path, then you multiply, oh, excuse me, here you multiply by p, here you multiply by q, and then you never return to 0, so now you have to multiply by 1/2 here and there. So the probability of green path divided by p is equal to probability of red path divided by q. And on the other hand, we know that if we sum we consider the sum over all paths that end at y and hit 0, or all paths that ends at negative y, then you obtain this value. So the probability that xn is y and you hit 0 before instant n, okay, 1 over p is equal to 1 over q. Probability xn is negative y. You may write this, you may not write this, okay, is x, and sum of this probability and this probability is equal to this. Then after, so it's linear equation. It's linear equation, and if you solve this linear equation, you may see that this probability is okay, sorry, maybe certain mistakes. Oh, one moment. So I2 is to P. Ah, uh, something went wrong. One moment. Excuse me. I made a typo here. This probability is equal. This probability is equal to psi n y plus x. Yes. So yes, I'm very sorry. So probability that you start from x and reflected random walk ends here is equal to probability that initial random walk ends here multiplied by 2. Yes. So yes, we have this relation. This probability plus this probability is equal to this probability or this probability, and solving this system of two linear equations, you indeed arrive to this formula. Well, I'm very sorry. I made a typo at the very beginning, so I don't have to write here the n y minus x. Okay, so the theorem is proved. We calculated at least, okay, we 1/4 of the theorem is proved, you need to calculate some three other probabilities. Well, but the way of proof is the same. You have to consider variance x and y, both of them negative, or one is negative, one is positive, and then compare with probability for simple reflected random walk, and then you'll get the results. Well, we so we receive this formula, and the next question is, what is a scaling limit of x and t divided by square root of n? And we know that if we start from 0, and if we consider simple random walk, then s and t divided by square root of n, if t is fixed, converges to Gaussian random variable, zero mean, variance t. And for this, the corresponding probability was psi n t, okay, integer part of the point that probability that you start from 0 and hit that is equal to psi n t. Let me write integer part of that. And you see this function psi n in this formula. And well, result or exercise, which is believable, is this. Assume that xn is a sequence of integer numbers such that xn divided by square root of n converges to x real number as n goes to infinity. We consider sequence of random walks with transition probabilities 1/2 everywhere except of 0 and p and q at 0, such that xn of 0 is xn. Then the scaling limit of x and t divided by square root of n exists. So let me denote by the limiting random variable like w skew of t, where w skew of t has the following density. And the answer is easy to guess. The answer is easy to guess. Well, xn of 0 is xn. When you divide by square root of n, you get x. And we know from the Moivre-Laplace limiting theorem that some scalings of this psi n are Gaussian. Well, and we know that these psi n are transition probabilities of unperturbed random walk, and unperturbed random walk converges to Gaussian distribution. So the density will be like this. And the formula is phi t of y minus x plus 2 pi minus 1, or p minus q if you wish, times sine of y, and times psi t of absolute value of y plus absolute value of x for all y and x positive, where psi t of z is a Gaussian density 2pt e to the minus z squared over 2t. T is positive, z is real. Well, just few words. How to prove this? Convergence, weak convergence of random variable is equivalent to convergence of their distribution functions for all points where the distribution function of the limiting random variable is continuous. So I state that the limit random variable has a density. Actually, the question is to verify that this is a density. So we need to prove that probability that xn of nt over square root of n less than or equal to z converges to integral from negative infinity to z. This density, so let me denote it by ptxy, ptxy dy. Well, this ptxy is the sum of two terms. The first one is this. And the question, is it obvious that and what is this? This is a sum of over all z tilde less than or equal to z times square root of n, probability that this, you start from xn, you end at z, and you make nt steps. You use the formula, you have psi, and for psi's, you know that the answer is integral of this. So you have to prove convergence of these to certain integral, and you know that sum of psi's converge to integral of Gaussian density. There is only one problem. The problem is with this sign, and well, to be honest, sine is discontinuous function at 0. And there are two ways how this problem can be solved. Either use certain asymptotics. Okay, you may use De Moivre-Laplace local limit theorems. You know asymptotics of this psi's, and then you have to show that these sums looks like integral sums of this density, and you have to care about a point 0. Y is 0 when this density is discontinuous, and well, it can be done, but at least the corresponding result is natural. It's natural to expect. And imported exercises are these. at first, show that this function is indeed a density of a random variable. Show that psi t y minus x plus 2p minus 1 sine of y phi t y plus absolute value of x is a density. Is a density if p in 0, 1. Second, actually integral of this function with respect to y is equal to 1 for all t x, for all t positive, x real numbers, and all p in R. So integral of this function is positive for all p. The third. Okay, if and the first is if is a density if and only if p in 0, 1. So this integral is 1 for all p. So this means that if p is not in 0, 1, then this function may be negative. And the third, verify the Chapman-Kolmogorov. Chapman-Kolmogorov equation for this density. Well, for p in 0, 1. So there exists a Markov process with this transition density. And there is a name of Markov process with this transition density, and the name is skew Brownian motion. A skew Brownian motion with parameter p, with parameter gamma in negative 1, 1 is a Markov process with transition probability density function that is given by the following formula: phi t y minus x plus gamma. So gamma is to p minus 1. If p in 0, 1, then to p minus 1 is between negative 1 and 1. Gamma sine y phi t of absolute value of y plus absolute value of x. Okay. And well, we know that this is, okay, if you solve this exercise, then you will see that this is a density. Then there is Chapman-Kolmogorov equation. And another exercise that proves that a skew Brownian motion with any parameter is a continuous process. Or it has continuous modification. So has continuous modification. Well, what are the ways? What are the possible ways of proof? The first one is this. How do we prove continuity of a Brownian motion? We applied Kolmogorov continuity criterion. We calculated moments, And then we prove that expectation of that there are alpha and beta such that expectation of xt minus xs less than or equal some universal constant times t minus s to the power 1 plus beta, where alpha and beta are positive. So if you find a constant c, alpha and beta such that for every s and t you have this inequality for skew Brownian motion or for some other process, then you get the continuity. And when you discuss Markov processes, then it is sufficient to prove that, so this is a hint that for every x, and for every t, so if x of s is, so if you have this to the power alpha, x0 is x less than or equal to ct to the power 1 plus beta, where c is the universal constant, then you get this inequality. And well, you have density, so theoretically it is not so complicated to get this estimate and then use conditional expectations and to receive this estimate, and hence continuity. Maybe the last remark. Okay, if you show, so these are universal statements. This is for all processes X, and this sufficient condition if for Markov. So please think why this is sufficient. And the general question is, okay, one-dimensional distribution converge to one-dimensional distribution of a skew Brownian motion. Do we have convergence of scalings of random walks? Do you have functional limit theorems? Well, the answer is yes. We will discuss some theorems and construction of skew Brownian motion on the next lesson. So thank you for your attention and see you in a week.
Thank you.
Goodbye.
Goodbye.